All right, so oh, that's the wrong class. No wonder it looked weird. Um, so to take up where we left off last night, here's this beautiful little drawing that I had up for you last night, and just kind of I guess look at it there. Again, binomial, two outcomes. You play a fixed number of times, independent trials. Each probability remains constant every time. That's true for the multinomial as well, except this is three or more outcomes. This is two outcomes exactly. Tonight we're going to be discussing the hypergeometric, which could mimic either one of those two, but from the standpoint that where they vary differently is the fact that they're not independent. Again, this idea of you sampling from a small candy dish. Negative binomial, two outcomes, independent. That is, probabilities do not change, but instead of playing a given number of times, you play until you win X number of times. And then geometric, of course, play until you win one time exactly. Okay? And we're going to talk a little bit also about Poisson tonight. So first, I guess, we'll do hypergeometric. So here's this bucket of M&Ms. Now, see, there's not too many in here. I'm just going to write 6 black M&Ms, 3 red, 2 blue, no, I don't know, 10, let's do 10 blue, sure. And, I don't know, 6 green, 5 orange. Alright, so let's reach in, let's take 5 of these M&Ms. Okay, if I do that, okay, what's the probability that I get 2 black, 2 blue, 1 green? Now, inherent in that is the fact that I got 0 everybody else, okay? So we've done this before. In the jar, there's 5, that's 11, 21, 24. There's 30 marbles in the jar, 30 whatever, I don't remember what I called them now, but I'm choosing 5 of them. Of the blacks, there's 6 of them, I'm choosing 2 of them. Of the reds, I'm choosing none of them. Of the blue, I'm choosing 2. Of the green, what the Sam Hill does that mean? 6 choose 1. And 5 choose a goose egg. Remember that the numbers on the left on top add up to the numbers on the left on the bottom. The numbers on the right on top add up to the numbers on the right on the bottom. You're probably right if you did that. Okay? You could still screw it up, but that's probably right. So here, that's 1. This is also 1. This is 6. Whenever you can, cut that down so you don't have to kind of dink around with that. I'm going to bust out the calculator real quick. You do whatever you like. It doesn't matter to me which of these things you use. So what I normally do, second math 7, and then down here this guy, and I just go 6, 2. All right, hit enter, and then I just go back and edit what I don't want. So now I want this to be 10, 2 here. That's 41. Stupid. Why don't you try 10? Attaboy. And then why don't you try, I already said what that is, and then why don't you do 30, choose 5 while you're at it. Alright, so it looks like it's 18 times 1, obviously, times 45. No, it's not 18, it's 15. 15 times 45 times 6 on top, divided by that nasty mess. And so the probability is that, or if you prefer, probability is about 2.8%. And whenever we do multinomials, the probabilities are going to be pretty dadgum tiny. They're just pretty dadgum tiny. Not multinomials or hypergeometrics. They tend to be fairly tiny probabilities. Okay, multinomials in particular, but hypergeometrics tend to be that way too. Even though this is a fairly kind of expected one to happen. I mean, it's not absurd that I get 2 blues. Maybe it's a little weird that I didn't get an orange, but I got 2 blacks. Maybe it's a little weirder than there. But again, it's not terribly out of the realm of thinking to do this guy. So that is how you do the the hypergeometric in the case that looks vaguely. Notice how this looks vaguely multinomial. That is, I was asking about blacks and blues and greens. But what if I said to you, hey, listen, I'm going to take 6 marbles out, 6 marbles, or whatever these are. What's the probability that I get no, or well, let's just say the probability I get 2 greens. Well, Jay, you didn't say anything about the other ones. That's right, but this is a binomial looking setup. So of the 30 marbles in the jar, I'm taking 6 of them. That's still my denominator. Of the marbles in the jar, 6 of them are green, and 24 of them are not green. A lot of people will forget about this aspect here. Well, you said you want 2 green. I did. But it's 6 choose 2, which I already know what the answer to that is, times this thing. 24 choose 4 is not a small number. It's a fairly healthy number. I don't know what it is, but I just know that that's a true statement. Come up here and grab one of these dudes. Bam. So I'll do 30 choose 6. That's my denominator. There is 593755. And then, of course, 16 choose 2. I think we said was 18 a minute ago, but I'll do it. I'll run up here and grab it. 6 choose 2 was 15. And then let's come back in here and do 24 choose 4. So hit that, times it by 15, divide it by that fella, and you'll see that you get this. I'll just rewrite it like that. It's 50. I'll just actually do it like that. I'm too lazy. There's the answer, and then I'm just going to go diamond enter. No, I'm not. No, I'm not. I'm going to grab this guy here, go diamond enter, and it's going to be about 26.8%. Okay. Again, this is the binomial looking version of this situation. Now, could a person ask, so the problem is something like this, what's the probability I get no more than? No more than, I don't know, 2 greens. Well, yes. Doesn't that sound like a CDF? It does. Is there such a thing? No, not really. So you mean to tell me that you're going to make me do this, and this, and this? Yes. But I already know this one is about 26.8%. I just found that one a minute ago, right? So if you think about it, the denominator is the same every time. It's 30 choose 6. But on top this time I'm going to have, in this case, I'm going to have 6 choose 1 times 24 choose 5. And then, of course, what I'm going to end up actually doing is this. I'm just going to write it like this, even though I already have this part here. What I'm going to say is they all have the same denominator, so a person could write it like this. You don't have to. You can actually do them all out however you choose. But this is the idea. Now, remember, this is just 6 choose 0 is 1. So this is really just 24 choose 6. This is 6. And then, of course, we already know what that number is. Okay, so I'm going to go back into the calculator here. And I'm going to go maybe I should write these down. So there's 24 choose 4 times 15 we said. So this was 159390 plus, and then go grab that again. So now I want 24 choose 5, but times by 6 this time. So that's 255024. And then the other one is just 24 choose 6. 134596. 134596. So if you add those guys together, that's the total possible combination. So it's this guy plus this one plus this one. So 549010, 549010 over 30 choose 6, which I wrote down somewhere momentarily a minute ago or 5 ago. Maybe I didn't actually do it. Maybe I just thought I did. Did I do it? Oh yeah, I did. 593775. Okay. And so if you look at that, well, that's most of it, yes? Woo, doggy. Okay, so it's that guy there divided by 593. Nope, wait, what just happened? Okay, hit enter. Sure. Divide by 0.593775. Decimal. Bam. So about 92.5% or thereabouts chance of this happening. Okay? Well, lovely. What if I wanted to have more than 2 greens? Well, you know, you can see that it's 7.5%, right? It's the rest of it. So I would never ask you for very many of these guys because that's just brutal. So yeah. But I might, so pay attention to that. Again, the difference between these guys is that the hypergeometric is they are dependent probabilities, or in other words, when you take one out, you're not putting it back in, you're altering the probabilities. Now, a Poisson distribution talks about a Poisson process. Okay, and your book describes that. It's on page, oh geez, what page is it on? Page, yes, there it is. It's on page, my glasses on, 161. Okay, so it says the number of outcomes occurring in one time interval or specific region of space is independent of the number that occur in any other disjoint interval or space. Okay, so in other words, it has no memory. So again, yesterday I talked about here's a stretch of Portland Road, potholes, potholes, potholes. Notice that that's a particular region. Let's say 1 mile. Okay, the number that occur in that mile are independent of the number that occur in this mile, are independent of the ones that occur in this mile. That's the idea of a Poisson process. It's the idea that if you work at a call center, how many calls do we average 5 calls an hour or something like that, or 52 calls an hour, or whatever it happens to be. You know, sometime, or if you, by the way, if you worked at, you wouldn't say this necessarily about, like if you worked at a restaurant, you wouldn't say it over the course of the day, but you could say, look, during the lunch rush, we average this many customers per hour. And then, you know, if you worked at a restaurant, I mean, back in college, I did the whole Subway thing for a year. And I worked from like 6 o'clock at night to midnight or 2 in the morning. And there were some nights that you were just slammed at dinner time, which made, okay, you're like, okay, well, sure, you know, you sell quite a few sandwiches. But some nights it just never shuts down. Like the whole night long, 2 in the morning, people are coming in to buy sandwiches. And you're like, this is so weird to me. And so for me, it was my shift I would compare, right? And I wouldn't necessarily compare the 6 o'clock or dinner shift because there's more of us working there. After 8 o'clock, I was by myself for the last 4 hours or 6 hours, which was kind of boring but kind of nice too. But I could have compared, like, you know, every night of the week that I worked, I could have compared them. I could compare Saturday nights to Saturday nights going forward. I could compare, you know, regular, you know, Monday through Thursday nights. I could compare them. We average a certain amount of sales every hour from 8 to midnight, whatever it happens to be. And from night to night, from hour to hour, those things are independent. For whatever reason, there might be some, you know, there's some huge deal tonight, so everyone's buying sandwiches, or there's a parade, or, you know, whatever there happens to be. The probability that a single occurrence or single outcome will occur during a very short time interval or in a small region is proportional to the length of time interval or the size of that region, and does not depend on the number of outcomes occurring outside that time interval or region. So you're like, well, Jay, what does that mean? Well, for instance, say we average 2 potholes per block or whatever, per block. Okay? And so like, well, what if it's less than a block, Jay? What if it's a quarter of a block? Well, then it's 2 per 1 block is equal to X out of a quarter of a block, right? And so you're like, that's a block. Stupid. There you go. And so you cross, multiply, and divide, and you get like what you'd expect of what, a half of a pothole in a quarter of a block. Okay? That's what you'd average. That's the idea of it. It's proportional, we say. Okay? And then the probability that more than one outcome will occur in such a short time interval or fall in a short region of space is negligible. Okay? In other words, it would be really odd if you had, like, you know, several, like, say this is a quarter block or a half block. It's a tiny amount of time. If you really partitioned it down to a teensy tiny amount, the probability that you get 2 of them in such a tiny amount is pretty small. In other words, what it's saying to us. Okay? The big news is this deal right here, this proportionality constant. That's the big news. And the idea that one time interval is independent of another. That sounds very similar to a binomial distribution, because again, they are related. Okay? So in a situation like this, you could say something like this. So if we knew that we average 10 calls per hour on some phone line, whatever it is, okay, what is the probability that we will receive 28 calls in 3 hours? Okay, that might be the question I'm asking you, okay? Well, in 3 hours, I feel like I would have expected 30 calls, yes? And so that's exactly right. That's the proportionality piece of this. This one's easy to do because, 3 times, obviously. So we would have expected 30 calls. What is that? What do we call this expected value? Oh, that's right, mu. And so that's where it comes into play here. Now, the function, the probability of the Poisson distribution looks like this. And it's excuse me. They write it like this. And I don't prefer to write it that way. That's just how your book writes it. I prefer to write it this way. Just the idea that the probability that I get X, given that I was expecting mu. The reason I don't really like to write, I like kind of writing it that way because it gives me that idea that I expected mu of them to happen. So it's given that I expected that to happen. It's not a true given statement. That's why books usually use a semicolon. Okay? But it's equal to, and then this is the formula. And you're like, wait, what? Yes. E to the minus mu. Mu to the x over x factorial. Just like that. Okay? And so here's the game. X is the number of things that can occur. It could be 0. You could have 0 calls. You could have 1 call, 2 calls, 3 calls, ... forever. Again, it's a discrete distribution. Okay? And that's the game. Now, in this situation here, what I'm saying is what's the probability I get 28, seen as how I was expecting 30. Well, it would be e to the minus 30 times 30 to the 28th power over 28 factorial. Okay, so I'll show you on the calculator first how I do it, and then I'll show you that Excel and the calculators will both do these with PDFs and CDFs. Oh, what a mess. Forgot to hit enter. It's about a 7% chance of that happening. Okay? Now, on the calculator, and everything will be exactly where it was yesterday. So in this calculator, it's going to be in the stats list editor. For the 8384s, you're going to go to distribution again. So second vars. Here we are. So we're down into here. If you scroll down a ways, you will see the Poisson PDF. It wants to know what lambda is. Now, some books, including yours, use mu, which makes perfect sense because it's an expected value. We would have expected 30 potholes. That makes sense. A lot of other books and the TI calculator use lambda instead of mu. So I expect 30. What's the probability that I get 28? Okay. So on your TI 8384 calculators, I'll show you what that would look like in a second. You see it's 7%. That's exactly what we got. On your TI calculator, it's on your TI 8384s, it's just going to be Poisson PDF, and you're just going to go 30, 28. Okay. I always forget, to be quite honest with you, which one goes in first. I just do, and so when this happens, I either grab my 89 and double check myself, or I do one by hand. And I see that it comes out the same as doing it by hand the first time. And then I feel very confident in myself going forward. But it's one of those deals, you don't use it every day. Like once a year you go, oh, I need to do some Poisson PDFs now. All right, cool. Bam! Okay? So there it is. Now, you're like, well, I saw the CDF too, Jay. Yeah, that's right. So what if I said to you, what's the probability that we get more than 28 calls, or yeah, more than 28 calls in 3 hours? Yeah, now you're well aware that, you know, you could maybe get 30 calls, or 31 or 32, or maybe even 35, 38 maybe even. You're not going to get 50 calls in 3 hours. The probability of that happening is ridiculous. In theory, you could get 150, 292. You could get, but they're not going to happen, friend. So when you think about this, most of the probability is going to be centered right around 30. Again, we expect 30 calls. So most of the probabilities will be like on 25, 26, 27, maybe up to 35. Like 99% of your probability or better is going to lie in this region in here. And you know, like you're not going to get 0 phone calls. You're not going to get 100 phone calls. It's all going to be in this tightly packed region. And I don't mean to make you think that it's like I went 5 on either side of it on purpose. I'm just saying that it's going to be fairly tightly packed to what we would have expected at that point. Okay? So this looks like a CDF to me. This sounds like x is greater than 28. What is the opposite of that? I feel like it's the probability that x is less than or equal to 28. Well, by George, that right there is a CDF by definition. So let's go find him. So I'm going to go back the other way here. I feel like boom, boom, boom. And escape, and this, and a Poisson CDF. Okay. And notice that didn't change on the lambda. I'm going to leave it as 0, and I'm going to go up to 28. This is what the calculator will give me. And the computer, I mean, when I do a CDF in a minute in Excel, is also what the TI-83 will give you. So this is the probability is less than or equal to 28 is 40%. That means 1 minus 40% or 60% is greater than that. Now someone might well ask, and it would be a great question by the way, what if I really wanted to go with the upper bound? What upper bound would I put into that? Well, it goes all the way to infinity, but I dare you to put infinity in there. Well, you don't have to, friend. I would wager that there's really no difference in letting it go all the way to infinity or stopping at 50. And lo and behold, what do you know? So that's about, oh, wait, what's wrong with that? What's wrong with that? Darn it! Did you see what I did wrong? Do you see it? I do. It's a little embarrassing, to be quite honest with you. It's a little embarrassing. Mr. Groom, you should not have used 28 as your lower bound, you idiot. You should have used 27 as your lower. I'm sorry, 29 as your lower bound, because we're going from 29 on up. Anyway, if I do this correctly, if I don't screw it up this time, I should get basically 60%. So that we had 40.4% a minute ago. That's the opposite of 40.4%. Are you with me? So that's exactly what I would have gotten. You're like, well, what if I increased it to 1,000 or 1,000,000 or something? Well, go right ahead. It isn't going to change anything, probabilistically speaking. But I wouldn't do that. I would just go with the 0 on up to 28 routine, because to me that's just a better way of learning the material. And so even if you wanted to go above it, you just go from 0 up to 28, and then just do 1 minus that. To me, that's just a better way to go. Okay. Now, in Excel or Google Sheets, whichever you happen to have, it's all the same for this particular solution. Okay. And boom, 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 boom. So equals Poisson distribution right there. Okay. So x, well, 28. Okay. The mean 30. Notice how that's bass-ackwards compared to what the computer asked for, or the calculator. There's my 7% that we did a minute ago. If I say cumulative, this is a CDF function. There's my 40% that's less than. Okay, 1 minus, that's the rest of it. Okay, same exact deal. If you're going to do upper than, I would do 1 minus, just because, do it all in one shot. That's just me. Okay, that's the idea. Poisson distribution is pretty easy to do in that regard. We'll do another couple of examples of them so you can get the idea of what they sound like when you hear one of them. Again, I think we mentioned the other day that there was, oh, I think I talked about a tree problem or some such. I don't know. And my pen is dead. Piece of garbage. Uh-huh. All right, one moment, please, friends. Seriously, this is embarrassing. All right, we're back. Yeah, I don't know. Let's see. I don't know. Maybe you work for a copy editor, like you publish books or something, and you average, two typos per 5 pages or something. Okay, I don't know, something along those lines. Okay. Well, all right. So that seems relatively straightforward then. So if you sample, I don't know, 13 pages. Notice that that's a weird number. It's not like 40 pages or something like a normal person. I did that on purpose. What is the probability that you will see, 10 typos? I don't know. Let's find out. Well, I would have expected 2 per 5. See this? That's cool. And that's equal to 13 in x, yes? So that's 26 divided by 5, which is 5.2. I would have expected 5.2. Oh, I'm not going to ask about this. I'm going to change this to 7, if that's okay with you. I don't care. I'm doing it anyways. It's just a little closer. If I do 10, that's like double the amount of errors I would have expected. That's pretty much non-existent. That's going to happen. Okay. Somebody do this one. It's just going to be a little more fun. And so I bring up the old calculator. Again, you pick your poison on this deal, whichever you like. Literally pick your Poisson. Alrighty then. Sorry about that. So I would have expected 5.2, and I actually got, or I'm talking about getting 7 errors. And so you will see that's about 11.2% or thereabouts. Approximately 11.2%. Okay? Give or take. Again, probability that you get more than, or no, at least 4 errors. At least 4 errors. Jeez. Well, that's the probability that x is greater than or equal to 4, correct? That's what I want to solve for. So I know that plus the probability that x is less than 4 obviously adds up to 100%. This is not a CDF, but this is. Right? And so because I want to solve for this fellow, which I don't have a way to solve for him directly, I'm going to use the CDF to get there. So I'm going to actually use Excel this time. Oops, no, come back. So equals, you probably should have a keyboard to do that, Jay. Equals, and freaking thing hates me. Oh, there it goes. Equals Poisson dist, and I'm interested in getting 3, I said, and I would have expected 5.2, and yes, I'd like it cumulative, and I want to do 1 minus that fella, so 1 minus. So there's about a 76% chance that you will get at least 4 errors. Okay? Pretty easy to do. Whoopsie daisy. Alright, one more here. Right. Instagram averages 13 stupid questions per day. I always tell my kids that there's a difference between dumb and stupid. A dumb question means you don't know. A stupid question is something like this. They just got done talking for an hour and a half, or we've just been a week talking about something, and they're like, what's that? That'd be a stupid question, sir. So in 5 days, what's the probability that he will get 70 stupid questions? Okay, let's find out. I don't know. So again, 13 in one day, SQs in one day is equal to x over 5. Looks like I would have expected 65 stupid questions. And so, bam, out we go with this dealio. So F5, over the top, Poisson PDF. I would have expected 65. I'm asking about 70, I think is what I said, yes? Bam. So there's approximately a, what is that? I think that says 3.9, but my glasses aren't with me. I think that says about 3.9% chance of that happening. Okay? And again, pretty straightforward kind of deal. Now, interesting. What if I told you that you know, some family was, well, they were going to have 20 kids. They were going to have 20 kids. I'm not sure why they're going to. They're crazy. I don't know. What's the probability that they get 14 girls? I don't know. Now that's clearly binomial. So that would be 20 choose 14 times 0.5 to the 14 times 0.5 to the 6, yes? So that's clearly what it is. And of course I could just use the binomial dist to get that. And so I'm going to binomial PDF, so we're playing 20 times. Probability of success is 0.5, and we're interested in getting 14 girls. And voila, the answer is 0.0369. Okay? Nice. Well, the question I might have is, could I approximate this with a Poisson distribution? And the answer is, I certainly can. So, in 20 kids, how many girls would you expect? Well, you would expect 10 girls, right? Because you'd expect 50% of them. True? And so, let's see what happens here. If I go in and I approximate this with a Poisson, and there's no reason why I would ever do this one with a Poisson. I would wait to approximate a binomial with a Poisson if I was playing a game like thousands of times. So somewhere along the line I have to do like 1,000 factorial, okay? And those sorts of things. That's gross. Versus this, it's pretty straightforward. You're simply going to go, well, I would have expected 10, and I'm interested in getting 14. That's it. And you will see that it comes out to be 0.052. Now you're like, that's not a very good approximation, Jay. No, it's not, because this is still a fairly small sample size. Now, what if we just drew names out of a hat? We had people that worked, people's names out of a hat. And by the way, the population that we have is evenly split boys and girls. There's like, I don't know. Let's say there's, I don't know. Well, let's say we literally have 200,000 names to choose from. 200,000 or something. And we reach in, maybe it's that idea that we could select 1,000 of them. What's the probability? What's the probability that we get, 490 women? I don't know. Now think about what that would look like. This would be 1,000, choose 490. And again, this is I just said there's a big population. That's all that means. Ignore that for right now. It's just there's a lot of them, so I don't have to worry about changing the probability anywhere, if that makes sense. So I can do 0.5 to the 490 times 0.5 to the 510. This is a gross thing to figure out. Okay, now your calculator has a built-in function. And again, nowadays, there's almost no reason to ever think about doing this. I just think it's kind of neat to kind of go back and kind of, oh, that's neat. So we play 1,000 times. And I'm interested in 490. And, oops, no I'm not. 0.5, I mean. There we go. And 490. And I get 0.02. So about 2% chance of this happening. Okay. You get the same exact thing with a Poisson distribution. And you'll notice that as the sample size gets, as the numbers get larger, is a better approximation. Again, with small numbers, just use binomial. That's how everybody always did it anyways. So here you go. I would have expected 500 girls. What's the probability I get 490? And what do you know? It's 1.6%. Okay? And so as I say, as the numbers get larger, the approximation gets better. Okay? It's still never going to be perfect, but it's a lot better. And again, these aren't really that large of numbers. Okay? So if you'd taken this, if this was hundreds of thousands and this was tens of thousands or something, then it would really come out to be a start, or it would be just amazing how close they would be. Okay? Again, I just show you this because I think it's kind of neat to see, again, that idea, that back to that chart from yesterday. The reason we study these guys is they're all sort of related together. Okay? Anyway, that should take care of you. I will be sending out a assignment later this week, probably tomorrow actually. I'm just about done with it. And the quiz will be posted, I think, tomorrow as well. Gotcha. Bye.